And our third speaker for this session is Mu Yuan, who was just asking a question. Mu Yuan's a postdoc from the Chinese University of Hong Kong, and he's going to be talking about KV cache. Actually, this is a privacy talk, I guess, so it's super interesting as well. So slightly different than the other talks maybe, but it's another component in this whole world of AI technology, but now looking at the confidentiality side of things, and an interesting approach here.
Okay, thanks for the introduction. Good morning, everybody. I'm Yuan Mu from the Chinese University of Hong Kong, and today I'm excited to present our work, SIX, Stateless KV cache encoding for cloud-scale confidential transformer serving. This is a joint effort between the CUHK and the USTC. Okay. To begin with, when a user interacts with today very popular chatbots like the LLM or VLM, the request flows to the cloud model, which generates a response token by token. This auto-regressive process continues until an end-of-sequence token is produced. Think of it as a dialog loop, prompting tokens out repeated many times, sometimes across historical sessions. We already have very solid defenses for two phases, in transit with the network encryption and decryption, and at rest with storage encryption. However, these are industrial staples, but neither addresses the moment the model computes on plain text data. This is exactly where most real privacy incidents occur. So, the unsolved question is, how do we protect data in use during computation when the cloud GPU must process something sensitive? Today, computation usually happens in plain text, which directly exposes sensitive input and output to the cloud platform. Both input and outputs can be highly sensitive. For example, medical records in input prompts or proprietary code in responses when you do the code debugging, right? And organizations and the industry has learned this lesson from this hardware. Organizations like the Samsung have restricted the cloud chatbots after accidental code leakage. The takeaway is clear. A practical solution must protect both the input prompt and the generated outputs while serving remains efficient. Okay, to understand this problem, let's review how transformer serving actually runs. The core in transformer's attention is the matrix multiplication of QKV, as the formula shows. In the previous stage, we process the initial sequence of n tokens, for example. We compute per token queries, keys, and values with dimension d. You can think of shape like n times d for QKV activations, multiplied and combined into a contextualized result. This stage initializes the model's internal memory for the sequence. After preview, we enter the decode stage. Now we generate one token at a time. For each step, we form a 1 times d query for the next position and attend over all n previous keys and values. Then append the new token to the history. Crucially, the model's generation function depends on the accumulated state from previous steps. Okay. To avoid recomputing everything at each step, we cache per-layer keys and values as we go. This KV cache goes with sequenced length. After each decode step, we extend k and v from length n to n+1. The cache lives across all attention layers, and it dominates both latency and privacy risks. It is compact, information-dense state that lets the cloud keep generating. And this is why transformer serving is stateful. Future computation depends on the existing KV cache. A lot of system works like the InfiniGen and CacheGen optimizes KV cache communication and layout because it is in the crucial path. But from a privacy view, the same cache is a liability. If an untrusted cloud holds a usable KV cache, it can keep inferring information without you and potentially leak information about your data. Okay, let's enter our SIX solution. Our objective is very straightforward. We want to ensure the KV cache maintained by the cloud cannot perform inference independently. We accomplish this by using a layer-by-layer encoding in the previous stage. We start with tokenization and embedding and immediately apply an initial encoding that shuffles rows, adds noise, and applies linear obfuscations. From the start, the cloud only sees encoded activations. In step 1, the cloud still runs the standard linear projections to form the QKV, but on the encoded activation. Because the inputs are obfuscated, the projected QKV are invalid with respect to the true plaintext activation. In other words, the cloud can compute, but what it gets is not useful for real inference. Next, we use the user-generated keys to recover the valid QKV. This recovery is very lightweight and keyed. Without the keys, the cloud-side QKV remains invalid. With the keys, we just can map them back to the correct feature space. After recovery, we proceed as if we had run the standard model, except the cloud never had usable states. And after computing the per-layer results, we re-encode the activations before sending them back to the next layer's projections. Then we repeat layer by layer, project on the encoded activation, recover with keys, and compute and re-encode. This iterative layer-by-layer process ensures that what persists on the cloud between the layers is always encoded, never a usable state. By the end of the preview stage, every transform layer's KV cache that the cloud holds is invalid. The only place where the valid KV cache exists is on the user side, protected by keys. This establishes the core property we need. The cloud alone cannot continue inference meaningfully. To support flexibility and defense in depth, SX uses independently generated keys per transform layer. That means compromise of one layer's encoding does not expose others. The cloud still sees the per-layer caches, but they are encoded with unrelated keys, so there is no cross-layer shortcut to recover the sequence state. Now decoding must be efficient. So if we forced a full decode that at every layer and every state on the user side, communication cost will be explode. SX's trick is to selectively share the keys so that the cloud can unlock only the needed intermediate layers during decoding. This preserves speed while still keeping the cloud from reconstructing a fully valid global state. Okay, you might ask, does sharing those intermediate keys weaken our privacy? Our analysis and experiments show that sharing intermediate layers does not compromise the privacy. The cloud still lacks the combination of states necessary to perform the independent inference or to reconstruct sensitive content, both the input and output. And in short, we share just enough to be fast, but not enough to be dangerous. And in decoding stage, SCX uses the hybrid strategy centered on the first and the last layers. We begin with embedding and an initial linear obfuscation. This sets up the decode step so that only specific boundary layers, the input and output, need to perform user-cloud interactions, while intermediate layers can be processed by the cloud itself throughout the sequence generation. Step 1 of each decode iteration, we apply the QKV projection at the first layers. The projections computed on the encoded activation initially produce the invalid QKV. With the user keys, we can recover valid QKV for that layer only. Once we have valid QKV at the first layer, we can form a valid big KV view for the attention at that layer using the valid KV cache we held on the user side. Okay? The query for the new position and the key value sets combining the historical KV cache. This gives us the correct attention weights for the step, but only at the boundary we choose to unlock. We then run self-attention using the valid Q and the bracket KV sets. And the intermediate responses or representations used across layers remain feature space shuffled. That is, it is encoded. So while we compute a correct result for the step, the cloud never accumulates a globally valid cache across the entire model. After attention at the first layer, we re-encode activations before traversing intermediate layers. These layers operate on encoded tensors. and does not need to per-step interactions. At the last layer, we again use the keys to recover what is needed, finish the step, and then encode outputs before storage or the next iteration. Only the first and the last layer requires these user key protected user cloud interactions. Okay. This boundary-only design has a powerful effect on the communication efficiency. Classic stateful serving often implies work proportional to T times L over the full stack. In SX, because only the first and last layers need interaction per step and the intermediate states encoded, we reduce the communication complexity just to T plus L, the linear input and output lengths, not their product. How do we implement this in practice? We split the responsibilities. We use a trusted CPU TE, the trusted execution environment, manages user keys and the lightweight open or close operations at the boundary layers. The untrusted GPUs do the heavy matrix multiplication that is involved in the original transformer models on the encoded tensors. And this preserves GPU throughput while keeping the keys and the valid states confined to the trusted zone. We evaluate SX on a wide range of models, from quantized small ones like the Tiny Llama and Qianwen, to large models such as the 70 billion Llama 2, and MOE models like the Mixture, and even vision language model like the Lava. On accuracy, that is what we really care about. SX is effectively lossless. We see that tiny max absolute difference in the logits that are negligible within the typical logit range and attributable to hardware representation, not the method. On Wikitext 2, SX produced just identical generated tokens to the plaintext model for the tested setups. So privacy does not cost your inference or your model quality. And on privacy, we ask, what if someone just tries to generate some text using our SX encoded caches? The answer is the outputs are just meaningless. Token perplexities explodes and the embedding similarity collapse on Wikitest 2 and the narrative QA both datasets. The encoded caches are completely invalid for generation, and this empirically shows that the cloud itself cannot infer any private input or output without the user keys. Finally, the performance. We evaluate the preview TTFT, just time to first token, and the decode TPOT, time per output token. These two metrics. SX outperforms state-of-the-art crypto-based protocols and the CPU-only TEs by orders of magnitude. For instance, the state-of-the-art crypto protocol may only support a very short sequence, like the length is just 8, okay, and still takes hundreds of seconds per token, whereas SX stays close to the plaintext serving thanks to GPU compute on encoded data and the reduced communication complexity. Okay, to conclude, privacy has become the bottleneck for deploying cloud-based LLM service in sensitive domains. By customizing protocols to the unique structure and the unique pipeline of the auto-regressive generation of transformer models, we gain optimization opportunities far beyond generic cryptographic tools. And SX realizes scalable privacy-preserving transformer serving, ensuring that the key caches stored in the cloud are stateless and useless without user secrets. For more detailed and our theoretical proofs and more evaluation and our code, please see our paper and GitHub. Thank you very much. I'm happy to take any questions.
Thanks again. Another great talk. Any questions out here? It's very hard for me to see if anyone's. I have a kind of question which is a kind of boring question, which is, you could just run a regular transformer in a confidential Azure, for example, or any other confidential cloud platform, right? I mean, you know, you could just use the fact that there are.
Yeah, I think nowadays I did not see any commercial model that support confidential serving. But the Apple, they claim that they use the private cloud compute techniques that almostly based on the dedicated access control, not the protocol-based, but the hardware-based solution supported by the Apple. Yeah.
Right. Actually, sorry, I misunderstood. So you're right. You're protecting people from being able to unauthorized use of inference. That's what your system protects against. It's like saying you can only use this system if you have the right keys, which is slightly different. So that's actually very cool, I think. That's quite, and the efficiency was very high, which is very cool. Yeah.
And our system does not require any specific hardwares or any software stack.
There's one question up there, if you can bring a mic down, thanks.
So great talk. A simple question. Could you share some intuition behind why the performance is not dropping? Because if I understand it right, what kind of a token or the KV the model sees might be out of distribution, right? So if it's still, the performance is not dropping, it is handling it correct, why can't you just do this kind of end-to-end, just once encoding and give it all the jumbo tokens?
Yeah. Okay, I got it. For the performance guarantee, yes, that depends on our specific transformation design. And the reason is we do not accumulate the transformation errors. We just encode it and make the cloud side to compute and directly just decode and re-encode it. We just not, so the error will not accumulate across different operators. We do it very frequently. Yeah. So our performance is guaranteed, and it theoretically generates the equivalent output. Thank you very much.
Great. Let's thank the speaker again. Yep, more interesting work. Thanks.